Hello everyone. Today I'm going to discuss or present the solution to some equilibrium problems and one problem on internal force systems. So for a smooth right circular cylinder of radius r rests on a horizontal plane and is kept from rolling by a string AC of length 2r. A prismatic bar AB of length 3r and weight 200 newtons is hinged at A and leans against cylinder. Find the tension T induced in the string AC. So this is the figure. So first, let's draw the free body diagram of the, let's label some important elements of the entire system. So because this length of string is common and we can drop a vertical line which is equal to the length of the which is equal to the radius of the cylinder, and we call the angle here theta, then also perpendicular to the axis of the bar, that's this angle is also theta. Because the hypotenuse is common, 2r, the opposite is r for these two right triangles. So sine of theta equals r over 2r, so that means theta is 30 degrees. So the entire angle here that the uniform bar makes with the horizontal is 60 degrees. So for the bar, free body diagram of the heavy bar, let's denote the weight as W as the action force. It acts 1.5 of R from A because it acts at the center, and we have N sub C here. So this is 1.5 of R. The distance of N sub C from A is from this right triangle. It is equal to 2R hypotenuse times cosine of theta, or 2R cosine of 30 degrees. These are the expected component reactions of A. So this is 2R cosine theta. As I said earlier, this is equal to 60 degrees, the total angle with the horizontal for the bar, because theta is 30 degrees. So summation moment about point A equals 0, then counterclockwise positive, so we have NC times quantity 2R cosine 30 minus weight W times 1.5 cosine of 60 equals 0. So take note that W is equal to 200 newtons. So let's just denote it with W. So simplifying, cancelling out small r, then N sub C is square root of 3 over 4 of W. So for the free body diagram of the cylinder, so let us denote the weight of the cylinder as W sub C, then transmit N sub C, which makes a total angle with the string of 60 degrees. So the string also makes an angle with horizontal of 30 degrees, or theta. Therefore, the angle that N sub C makes with horizontal would also be 30 degrees, because this total angle here is 60 degrees, equal to this angle here. So summation forces horizontal, so W sub C is not uh, included in the equation, because our equation of statics is summation forces x0. So N sub C cosine 30, which is square root of 3 over 4 W cosine 30 minus T cosine of 30 equals 0. So cancel out cosine 30, so T is square root of 3 over 4 of W, and since W is 200 newtons, so tension is square root of 3 over 4 times 200. So T is equal to 86.6 newtons. So let's proceed. Problem 2, the boom BE of the stiff leg derrick shown is horizontal, and its projection on the XZ plane makes an angle of 30 degrees with the x-axis. The post AB is vertical and is supported in a ball and socket joint at A. The points A, C, and D are on the same horizontal plane. Determine the forces in legs BC, and BD, and the components of the bearing reaction at A. So this is the figure, and remember it is stated that this BE is horizontal parallel to the XZ plane, and it makes with the x-axis of an angle 30 degrees. So this is the projection of BE on the XY plane. The length of AE is also 4 meters. This is cosine 30 degrees. So for the components of tensions, so we have CX, CY, and CZ, as well as for at D, DX, DY, DZ. Remember that tension force is a two-force body. Then at A, let's assume these are the component reactions at A. So first, let's sum up moment about AZ axis so that we can set up an equation for CY and DY. And we only need CY and DY to solve for the tension for for leg of Derrick BC and for the leg of BD. Summation moment about AZ equals 0. So by right hand rule, we have CY times 2 plus DY times 2 minus 10 times 4 cosine 30 equals 0. So simplifying, CY plus DY equals 10 square root of 3, call that equation 1. Next, we sum up moment about the x-axis so that we only involve CY and DY as well as the moment of the 10 kilonewton load. So summation moment about AX axis equals 0 by the right hand rule. We have CY times 2 minus DY times 2, then plus 10 times 4 sine 30 equals 0. Simplifying, CY minus DY equals negative 10. Equation 2. So we add equations 1 and 2 to solve for CY. Then after that, we substitute the value of CY into equation 1 to solve for DY. So adding to C sub Y equals 10 square root of 3 minus 10. So C sub Y therefore is 3.66 kilonewtons. Then since substitute this value CY into equation 1, 3.66 plus DY equals 10 square root of 3. So D sub Y is equal to 13.66 kilonewtons. Now that we have found one component reaction, then we can solve for the force in its leg by similar ratio. So 3.66 as to 6 equals FBC as to square root of, this is distance BC. So if you go back to our we go back to our preceding if we go back to the preceding slides, the distance BC is equal to square root of 2 square plus 2 square plus 6 square plus 2 square. So that's it. So FBC therefore is equal to 4.046 kilonewtons tension. Then for FBD, so 13.66 as to 6 equals FBD as to square root of 2 square, 6 square plus 2 square. FBD and BC have the same length. So therefore FBD is 15.10 kilonewtons. Then we sum up, let's solve for CX and CZ. So by equal ratios. So 3.66 as to y distance 6 equals CX as to 2 equals CZ as to 2. So CX equals CZ equals 1.22 kilonewtons as indicated in the figure. Then 13.66 as to 6 equals dx as to 2 equals dz as to 2. So dx equals dz equals 4.553 kilonewtons. Then to solve for AX, we sum up forces along X equals 0. So we have AX minus CX minus DX equals 0. So this is CX, this is DX equals 0. So AX is equal to 5.773 kilonewtons, and that is directed towards the positive x-axis. Summation forces Y equals 0. So AY minus CY minus DY minus the load 10 equals 0. So AY is equal to 27.32 kilonewtons upward. Then for summation forces along Z equals 0. So CZ minus AZ minus DZ equals 0. So CZ minus AZ minus DZ equals 0. So AZ is equal to negative 3.33 kilonewtons. In our assumption, in the free body diagram, AZ is directed towards the negative z-axis. Since this is negative, it should be directed towards the positive z-axis. So AZ is 3.33 kilonewtons towards the positive z-axis. So that's the solution to problem 2. Let's proceed 3 on internal force systems. So determine the internal force systems acting on section 3 for the pin connected frame. So we have here the pin connected frame, and this is section 3. So all you have to do is to determine the reaction components at B, and take note that member BC is a two-force body because there is no external load in between these smooth pins. So since the arc is quarter circular arc, we expect that the reaction at B is pointing towards C. Likewise, the reaction at C is pointing towards B. And because they are equal, then and making 45 degrees with the horizontal, because this is 0.5 and 0.5, so we conclude that dy and dx are equal, and the angle that the force is directed along an axis which makes 45 degrees with the horizontal or with the vertical, the component reactions are equal. The magnitudes are equal. So summation moment about A equals 0 considering the whole system. Counterclockwise positive, so dy times 0.5. Since this is a couple, the loads constitute a couple, then dy times 0.5 equals clockwise moment, so 300 times minus 300 times 0.4 equals 0. Or if you sum up moment about A, so by times 0.5 plus 300 times 0.5 minus 300 times 0.9 equals 0. So the result is still the same. dy is equal to 240 newtons. Since, as I said, BC is a two-force body, so we expect that dx is also 240. AY is 240 downward, considering the whole system. So the proof that dx and dy are equal, you sum up moment about C. So bx times 0.5 minus 240 times 0.5 equals 0. So that proves that dx is also 240 newtons. So consider now the free body diagram of the portion B to 3, where 3 is revealed as a section. So these are the reactions at B, and the forces at 3 are the following: N3 perpendicular to the radius, then shear, assuming these are the directions as shown in the figure, because we can anticipate that these are the directions of these internal forces. And the moment should be counterclockwise because the moment of the 240 Newton force is great, or this horizontal force is greater than the moment of the vertical force. So this angle here is 40 degrees and the angle that entry makes with the horizontal is 50 degrees. So summation forces along x, so this is 0.5 sine 40, the horizontal distance from A to section 3 is 0.5 cosine 40. Summation forces x0, so n3 cosine 50 plus v3 cosine 40 equal minus 240 equals 0, so simplifying, n3 cosine 50 plus v3 cosine 40 equals 240. Let's call that equation 1. Summation forces y equals 0. So we have negative n3 sine of 50 plus v3 sine of 40 plus 240 equals 0. Then simplifying, negative n3 sine 50 plus v3 sine 40 equals negative 240. Equation 2. So solving these two equations, simultaneously, then we get n3 equals 338.1 newtons positive, so the assumed direction is correct. So this is compression, and v3 is 29.58 newtons, so that's also correct direction of v3. Then for m3, we sum up moment about section 3 equals 0. So assuming counterclockwise positive, so we have m3 plus 240 times 0.5 minus 0.5 cosine 40 minus 240 times 0.5 sine 40 equals 0. So solving for m3 is 49.06 Newton meter. Because it is positive, the assumed direction of m3 is correct. So you can also compute n3 by summing up moment about A, and if the answer is the same as 338.1, then these answers are correct. So I hope that you will also practice solving more on equilibrium systems and try to consider these internal force systems.